I'm Mitch Marks with HBK, and today I'm going to be presenting on simplifying motor inverter validation. So testing motors and inverters, making sure they work the way we want them to, by combining power analysis and data recording. What we find is that people use a lot of different tools for validation and for understanding their motors and inverters, and we think we can simplify this, and I'm going to present a case to you today. So topics for this session, we're going to do a quick review of electrification challenges, specifically centered around vehicle development. We're going to look at equipment needed to solve engineering problems. We're going to look at some ways tests can go wrong. We're going to look at eDrive power analysis and how this combination of power analysis and data recording can really help accelerate your testing. And then we're going to go over a couple examples. And let me test my pen. All right. Beautiful. Cool. So in electrification, we have a handful of challenges. We want to know, what's our battery life going to be? It's a big question. How long can our vehicle go? How long can it stay in the air? How long can it drive? What is our battery life? And kind of related to that is, what is the vehicle range? We want to know how long it'll last for the duty cycle, but we also want to know how far we're going to go and how efficient we're going to be, kind of hit that green checkbox. What's the experience? This is one I think we don't think about a whole lot. What's this vehicle going to sound and feel like? Are we going to trust it? Are we going to enjoy it? Vehicles have a really emotional response. How fast can we get to market? This is another one I think is really important right now. Everybody is rushing to get a vehicle out. And are we going to hit all these quality concerns on time? And are we going to beat our competitors? And then relating to validation, how much testing are we going to need? What are we going to need? Are we going to need new departments? So a lot of people are asking themselves right now, how do we go farther? How do we perform better? And how do we get to market faster? So hopefully we're going to help solve these. So in our electric powertrain, we have a battery, our DC power, we have an inverter. This is turning that DC battery into AC to excite the motor. We have our electric motor, and again, this is just a quick review. And then we have a gearbox, transmission in some cases, propeller, pick your poison. It's all the same at the end of the day. And from that DC energy, all the way to that mechanical output, that rotational speed, we want to minimize losses so that we can maximize range. We all want to have that most marketable range. And we have inverter losses we need to characterize, we have motor losses, and we have mechanical losses. And this is where vehicle range becomes a major development concern. Because like everything, there's only so many ways to fool Mother Nature. We have to make these really difficult engineering decisions. Maybe vehicle sound versus range. Maybe vehicle performance versus range. So we want to check those boxes and make sure guys like I myself have a long career ahead of us. In addition to range, though, like I said, we have these engineering challenges, and we need to weigh product experience. Can we tune that inverter to make the experience better? We have durability. It might get that range number, but what if the thing falls apart at the end of the day? That's no good either. Noise and vibration. This is really that experience of the vehicle. And the electric vehicle has some unappealing noises. Overall, it's very quiet, but the noises that there are in that really annoying range. And we can do things, again, to that inverter to help noise and vibration, but are we going to reduce range because of it? There's thermal considerations. There's system performance. So in this electric powertrain development, in addition to efficiency, experience, reliability are also concerns that really require extra validation. And all of these have different tools involved. I think you guys can see where this is going. So when we're doing all these tests, what do we really want to understand when we're doing validation? What are we looking to prove? Well, that vehicle efficiency, so we can get that range. We want to look at transients. So when we go to get that 0 to 60 and we step on the gas or the accelerator, we get that really nice takeoff. So when we're slowing down, we don't get another bad response. We want to look at failures and how we can push our devices to failure and know when they fail, understand the physics of failure so we can avoid it. It comes into that durability concern. And then we have the controls. How do we gracefully move through transients? How do we gracefully get the best efficiency? How do we avoid failure? And if you start thinking about transients, these are a fast phenomena compared to maybe a steady state efficiency. Failures are an extremely fast phenomena. And efficiency is compared to the other two, generally a slower measurement. Controls are a combination of fast and slow measurements. So we have many tests to achieve all of these that require accuracy and high sample rates. We need to measure very quickly to catch all these interesting transients. We need to test accurately so we can trust our range numbers. So there's going to be a little bit of a theme here. So what equipment do we need to solve these engineering problems? Get now into kind of the meat of it. Well, again, back to my battery, inverter, motor, transmission table. Well, on the DC side, we need voltage, current, temperature. On the AC side, we need voltage, current, temperature, efficiency, which is kind of a combination of those. Noise and vibration. We need to know the high-level commands. Some might call this CAN bus. And I'm sure we could find some other things to measure as well. On the electric machine, this is where we're turning that electrical energy into mechanical energy. It's a little more interesting. We now have torque and speed, temperature, efficiency, noise and vibration. And again, we might have some other signals of concern as well. And then on the gearbox or the output mechanical, torque, speed, temperature, efficiency, noise, and vibration. You can see here, this is a ton of measurements that need to be made for a simple characterization. And this electric powertrain is absolutely a mechanical system that is driven by electrical power. And we need to understand that electric side and that mechanical side. And there's a lot of new challenges that come along with that. Historically, the electric guys and the mechanical guys have really been separate entities. And now they come together and the two sides need to understand each other, need to be able to communicate with one another. Now, when we're doing these tests to look at all those variables, what kind of tests are we actually running? And here I have the title as measurement points time consuming. Well, again, it's an electromechanical system. Our motor and our inverter are going to perform differently. And when we do an efficiency map to really understand what the range of our vehicle is going to be, how efficient is it? You know, an efficiency map might have 200 points, 200 combinations of torque and speed that we want to understand the efficiency for. And we don't just do one efficiency map and we're done. The efficiency of that motor is very state dependent. Meaning that at different temperatures, we're going to have different efficiencies, different ranges. At different levels of magnetic saturation, we're going to have different efficiencies. At different battery voltages, we're going to have different efficiencies. And then obviously, every iteration of this is different efficiencies. So if we have this 200-point map that we're looking at 10 temperatures, 5 saturations, and 5 states of charge, we end up needing to measure 50,000 points. You take that 50,000 points and you look at how long would that take me if I did a 10-second measurement, and you're looking at about 13 days. If I did a 1-second measurement, it's about 13.9 hours. And if I take a 0.1 second measurement, that's 1.39 hours. Now, this is not considering heating up, cooling down, but these tests can take a very long period of time. And that being said, a lot of times engineers will take fewer points, so look at a smaller system, in order to reduce that test time. But it still takes a long, long time. And this is just for those range measurements. Every time we make a small change to affect noise and vibration, we need to rerun this or a subset of it. Every time we make a change to the topology, to the architecture, we need to rerun those. So tests can be very time consuming. And where I'm getting at with this is that we also have to do these control tests, these transient tests, these calibration tests. And if we can start to combine some of these tests, we can start to reduce that test time. We can start to reduce that time to market. We can include NVH in there. And these types of things as well, durability. we can again reduce the number of tests we're running, reduce the amount of equipment, and decrease that time to market, and really decrease the cost of development. Now, in a traditional system, for data acquisition, so we've covered sensors, we've covered the tests. What do we need to measure this? We would need a power analyzer to very accurately measure these electrical powers. We would need scopes to get these high-speed transients, get these inverter signals. And we likely need data recorders to get that durability or NVH information. So we end up having 3 pieces of equipment that need to run separate tests. Testing is time consuming and requires a variety of tools. So that's what I'm here to help you solve. So rather than having a lot of separate tools, using a piece of equipment that's made for motor testing can really help simplify this. So now we have nice animations of our powertrain. We have our battery, our inverter, our motor, and we can see all of these things are connected to one common system. And we can view all those things on a PC and give feedback to an automation system. Now we're looking at the voltage and current that's being measured. We're looking at the inverter voltage and currents, those are being measured. We're looking at the torque and speed, that's being measured. Winding temperatures, battery and inverter temperatures, vibrations, and inverter noise or motor noise can all come into one common system, and this is what we call our HBM eDrive. And what this allows is for you to simplify that measurement chain. While you're going through this long efficiency map, you can record all the data you need. You can take the electromechanical signals and you can really achieve that simplified test profile and accelerate that testing. All right, so eDrive, what is it? What does it do? So this is our power analyzer / data recorder. The eDrive system makes a really easy measurement of both electric and mechanical signals. So we can measure those high voltages, currents, but also torques, speeds, and a very high bandwidth and accuracy. Accelerometers, microphones, temperatures, CAN bus can all come in to one common measurement system, so you don't have a wide variety of boxes, which really allows you, again, to accelerate that measurement, to do multiple tests with one test run, and to really reduce that time to market. We make fast and accurate efficiency measurements. We use a technology called cycle detect, so we can measure points extremely quickly. So we can measure those efficiency points extremely quickly. Basically, we're able to take that 13-hour test or that 139-hour test and significantly reduce it. So go from maybe that 10-second measurement to that 0.1 second measurement. Again, we can bring in all those mechanical signals. We can characterize all those mechanical signals. We can measure more quickly, which is going to allow us, again, to speed up that testing and to have fewer pieces of equipment. We can future-proof your testing capabilities. What does this mean? We have a card-based chassis. So if today you're doing a system and you do not need noise and vibration, but tomorrow you do, you can add a card. Now you can do noise and vibration. Maybe now you need to do 2 motors instead of 1. You can add a card. Now you're measuring 6 phases instead of 9, or 9 phases instead of 6. Our testing is auditable, and this is really where the scope ability comes in. This is the power analysis, which we've just discussed in the previous 3 points. We record data at a high sample rate for all of our channels, and we can do that continuously. So we're storing all the data that's going into your measurement. What is this telling me? So if I sample each channel at 2 megasamples per second, and I can do that for a half hour, I can understand full drive cycles. So we're recording all that data and trying to displace that scope. Now you just have a power analyzer and a scope. You have your power test and all the data that went into it. You have a perfect transparency of what happened in your test. And we also give you all the equations. So you have the results, you have the data, and you have how you calculated the results. All in one package, recorded continuously, like a scope, like a data recorder, but with the accuracy of a power analyzer. And then we offer feedback control systems. So you have a dynamometer you can drop in, run very easily. And HBK is a company. We have acquisition systems, we have software, and we have sensors. So we're really trying to simplify that measurement chain. Again, all that data is recorded. We'll give you those public equations. Here's a screenshot from our PWM inverter. This is from our software. And we're storing all that data to disk at 2 megasamples per second. And that's for as long as you have hard drive space. You can rack up a ton of data if you want it. We have reduction methods if you don't. We have the calculated results. So you can know exactly what happened in your test. You have a perfect understanding. You can see the time periods we're averaging on. You can see how the equations are done. If somebody questions your results, you can have an answer for them. And we can correlate these test to models. And we can execute all these equations in the real time to cut down on post-process time. So we're really trying to accelerate the testing. Recorded data and equations make tests auditable, but they also allow you to displace your scope in a lot of circumstances. Again, reducing that amount of equipment, making testing simple. Our fast efficiency testing, we use a technology called cycle detect, where we look at the phase A current of our sine wave. We identify zero crossings, and we take 2 successive zero crossings, and we call that our half cycle. This is where we do our RMS, power, efficiency, and all of our calculations are done on this cycle basis. This allows us to test very quickly. In a couple of rotations of the machine, boom, you have an awesome result. And an example of that is seen below, where we have a machine that is at a constant torque, and we're stepping down in speed. And so I have my speed in green, we can see that going down. I have my torque in pink, pretty constant. When I change points, we get a little spike there. And we can see my voltage and current, so basically my electrical power decreasing. We can see my power is decreasing, and we can see my efficiency is kind of rolling off. Now, what's special about this? Well, if we look at the time period, each one of these divisions is 5 seconds. And we can see I have 1, 2, 3, 3.5 measurements per division. We're basically taking a measurement every 2 seconds. We're getting a really high quality, very high accuracy measurement every 2 seconds. And we have all that recorded data, so we can go back and do our analysis. So we can go back and review our results. So we can do that scope test, that electromechanical test, and that efficiency test all at once and do it very quickly. So there's really no measurement settling time with that cycle detect. So you can test as fast as your dyno and acquire all that data for review. So cycle detect combined with all that data recording really gives you the fastest possible power analysis. All right, so correcting tests with data. What does this mean? Let's look at what this means. So in the world of power analyzers, the time period over which you average power, what we use the cycle detect for, matters. And now we track that cycle. We track if that cycle is correct or not. Every power analyzer is going to mess up their time period. We are just going to give you the information that allows you to know if you messed up that time period. So here is an example of some bad cycles. And here's my settings for my cycle detector for the bad cycles. And I'm following my cycle check. And we can see I get these big spikes. These are telling me that I took double cycles. But then we have this really steady area, and then I start to speed down. And then I have these just zero. I have these missed cycles. Now these are kind of corner case points, but I selected them for a reason. Because this was a really weird excited machine where it had this heart-shaped PWM. And if I zoom in on my missed cycles and I actually look at the data, and again, these cycles are what our powers are being averaged on. If the cycle's wrong, the power's wrong. We can see that really near zero, I have this little heart shape and it's crossing zero, sure enough. And I'm getting these bad cycles. Well, that's okay. Now I know where I'm getting them wrong. Really low power, low speed. Also, I look at the other segment and I can see, okay, this is basically no current being applied. I'm not catching these cycles because they're too small. We have a hysteresis band. So I make some corrections to my cycle detector. I change the hysteresis levels, I change the cutoffs, and well, I left the frequency the same. And we can see now in my pink area, I now have all my cycles correct. Boom, we're tracking. We don't have any more of these spikes. We don't have any more of these dips. And again, I look at my pink area, now we're tracking that cycle beautifully. Now we're tracking that really low power beautifully. I have the data, I have the equations, I can edit that, and now I've just saved myself 2 hours on a dyno. Because I had data, I was able to review and not have to rerun that test. So the raw data and editable equations really save us in that regard. Rerun tests without physically rerunning them. And this is because we're transparent. We're telling you that result was wrong. You need to rerun it, but you can do it in data. All right, here's some examples of advanced analysis and with some data recording. So many people run efficiency maps. Power analyzer data is often run for efficiency maps. And a lot of times people want to just take a ton of data. So I think this is something like 300 set points. We have our currents, our voltages, our torques in pink, and our speeds in green. And each one of these segments is about 15, 20 points. So we're recording that data, and here's a zoom section of one of these data points, and we're stepping through that. And because we have that data, because we're doing all those calculations, we can take that and plot an efficiency map, or we can plot a copper loss map, iron loss map. You can plot whatever map you want. And if you took all this data live, but a month from now, you want to do a different type of map, you want to do a different type of analysis, you can take that raw data, recalculate it, and run your other maps. You have all the data, so now or later, you can use that data to understand your machine. The power analyzer is used for efficiency maps. Now we're taking all that mechanical data as well, and we're recording it. And here's an example of recording an NVH test with torque ripple, the dynamic torque. We're recording voltages, we're recording currents, and we're recording dynamic torque. And then we can take that data and we can do NVH analysis with it. We can run color maps. We can look and find the order content of our torques and correlate that back to accelerometers, to microphones. So different groups, not just powertrain, NVH, all of these groups can use that powertrain data to understand their machine. Inverters are order-based phenomena. We can use that data to understand our noises, understand our vibrations, understand our experience. Again, fewer pieces of equipment, fewer tests, more data. It's really going to accelerate your time to market with a better product. Complex analysis. We all have these motor nerd guys, myself included, who just can speak a completely different languages. We have a complex power flows where we might have one battery with multiple motors. We have guys who want to look at how the machine responds to accelerations, decelerations, and they want to do things like the space vector analysis or the DQ0. And they want to take this information, understand things like their iron loss, their copper loss. Because they have the data, maybe the powertrain guys ran this, they can take all that data, understand how the machine responds to controls in that same test. They can do it live, or they can do it with data afterwards. Take it into whatever post-processing program they want and really understand that machine. Even for complex systems, even for electromechanical systems, you can have all that information. Large and small systems require control analysis to really make sure everything works out. And for a large system, let's say it's a drone, you can take all these different motors and understand system level control. Lastly, post-process data. We can take all of this data, run it, and it can be significant volumes. And you can correlate models to fleet data. You can run what if analysis, or maybe you change a couple of variables. It's not measured, you're kind of simulating it. You can compare many tests, you can do batch processing. And you do cloud integration. And here I have featured some flows from our GlyphWorks software, where you can take all your data and really run it through whatever batch process you want. Compare it to fleet data, compare it to road data, compare it to whatever you want, models. And really understand that system. And again, take all this data, do something valuable with it, turn that data to decisions, and analyze these large volumes of data quickly. But anyhow, thank you for your time. I hope I've shown you that HBK can help you solve your development issues by combining power analysis and data recording into one simple electromechanical system. If you'd like to reach out to me, please feel free to find me on LinkedIn, or you can email me here. And with that, thank you for your time.